Welcome! In this video, we will take a closer look at how classification intuitively works. We will do this by using the iris dataset. In this video, we will first download the iris dataset. Afterwards, we will try to understand how classification intuitively works using a very simple algorithm that was already developed in the 50s. We will implement this very simple algorithm, which is called Rosenblatt's perceptron algorithm, in Excel. We will then continue on to using Microsoft Azure ML Studio. We will then also take a first glimpse at the receiver operator heuristic curve, which is quite important when evaluating different kinds of classifiers and comparing their performance against each other. We will also take a first brief look at the confusion matrix, which can be quite confusing like the name says at first. Now, because this is an introduction into classification, we choose to use a very simple data set. This data set has only two flowers in it, and it has two covariates, so it has only two x variables. One could also say that this data set, the iris data set, is like the hello world for programming in machine learning. Hello world in programming actually just means that when you code the first line, that you try to print the statement hello world, which is like really easy, right? So we get the data by clicking on here. This links us to the OneDrive folder. The iris dataset which we are going to use is located in the folder iris. We then download the iris.xlsx file without the solution. Do so by clicking on the upper right and downloading the Excel file. We can then open the Excel file. And enable the editing. Now in the Excel file we just opened, we can see that we have three columns. In the first column we have our first x variable. It is called sepal length. And in the second column we have a variable called petal length. We will see in a moment what this refers to, the sepal and petal length. If you're no flower expert, I think it's quite hard to imagine what this could mean. In the third column, in the column C, we have the species of the flower. Now we have two species. One species is called versicolor and the other species is called setosa. In the figure below, we plotted for you the 100 iris flowers, which consist of 50 setosa and 50 versicolor flowers. In the graph below, you see that the versicolor flowers are indicated by a red dot, whereas the setosa flowers are indicated by a blue dot. Now just assume that you have a new flower which comes, which you are uncertain what type of flower that is, and you can only observe the sepal length and the petal length of that new flower. And now you're curious about, without having any prior knowledge about, just by looking at flowers, what kind of type of flower this could be, by classifying it into these two types of flowers, so either setosa or versicolor, just based on these two x variables that we have, sepal length and petal length. Now for a potential business project, this could relate to, as we already saw in the prior videos about touching data and analyzing the patterns with the band clone case. Whether or not a new prospective client is a good risk, that means that he will be able to pay back his loan in the future, or is a bad risk, which means that he will probably default in the future. All problems of this kind generally fall under the area of classification. This makes classification such an important topic within machine learning. Now I promised you I would talk a bit more about the two variables we have in our data set. From the pictures you can see on this slide, we see that we have petals and we have sepals. Petals and sepals are two different kinds of parts of flowers, and each of those parts have unique width and length. By looking at the two flowers, the iris setosa and the iris versicolor, we can see that these two flowers look different. And if you recall the figure on the prior slide, where we had a scatter plot, where we indicated which flower was which, just by observing the petal length and the sepal length, we were already able to do some kind of pattern recognition. Now, of course, we just don't want to look at the figure and draw a line by hand. We want to do this in a smart way. And we would like the computer to figure it out on its own. Because this is like an introductory example to machine learning, we only use 2 variables, but the full data set consists of 4 variables, also considering the width of the sepals and the petals. But here in our small toy example, we are only using the length. We are also able to show that just by considering the sepal and petal length, that we are already able to fully classify all the flowers in our sample. Now, in order to obtain classifications of new flowers, we need some form of codified knowledge. This just means that every point in the feature space is indicated by a class. So how do we do this? The actual knowledge is generated by the detective work of the algorithm. Knowledge just means that the algorithm is able to learn what kind of combinations of covariates, so what kind of values of sepal length and petal length are more probable of being represented by the species versicolor, for example. In our iris case, the feature space only consists of 2 x variables, right? This means that the feature space is a collection of 2 numbers, the sepal length and the petal length. So, for example, the sepal length is 6.1 millimeters and the petal length is 3.2 millimeters. We will now start to implement our first own classifier. This classifier is quite old. It was already invented back in the 50s by Frank Rosenblatt, and it was funded by the US Navy. You can also see on the picture on the right hand side, the Mark I machine that was actually able to compute this algorithm was quite huge. Today we are quite fortunate that we can replicate such an algorithm with a few simple lines of Excel. Now on this slide and the next slide, we have exercise number 3. In this exercise, we will implement Rosenblatt's perceptron algorithm in Excel. What I suggest you to do is to read these 2 slides, you go back and forth, and you pause the video. Because afterwards, I will show you how to solve it. But I think it's better for your own learning gain that you try to figure it out on yourself first. We start exercise 3 by creating a new column that replaces the setosa and the species variable by -1 and the versicolor species by +1. And we call the new column num label. We choose this -1 and +1 coding of the variable because we will choose a very simple boundary. In our score equation, which we will see shortly, we will see that we will classify a flower as versicolor if it is greater or equal to 0, and we will classify it as a setosa flower if the score is below 0. This minus and +1 just makes things a lot easier because computers don't calculate that well with letters. What you will also see quite frequently in classification exercises is that one category is coded as +1 and the other category is coded as 0. In our case, however, it makes more sense to code it as +1 and -1 because we need that simple boundary of 0 for the perceptron algorithm from Rosenblatt. Other coding choices of the species variable would also be acceptable, and other boundaries also. The algorithm would still work. We now create the new column in Excel. We need to assign versicolor in the species variable the numeric value of +1. And if it's setosa, we need to assign it the value of -1. We can do so by using Excel's if function. In this condition, it tests whether or not in the species variable versicolor the cell equals to versicolor, and if it does, we can type in 1, and if it does not equal versicolor, we can type in -1. We can now continue this formula. It stays valid for all entries, for all 100 entries of our dataset, by simply double-clicking on the cross. This translates our species variable into -1 and +1. We now continue by making 3 new columns, the columns being W0, W1, W2. These columns will represent the weights, and for the first row we will tell the algorithm that all the weights should equal 0. This represents that the algorithm is completely clueless. The algorithm, it can modify the weights in order to incorporate more knowledge about which attributes should belong to which species. We will see that the algorithm, it does so by incorporating new knowledge as it comes along, and in particular when it makes mistakes. We now create these 3 new weight columns and fill the first rows with 0. Now we will see that the W0 column that represents the intercept, we will at the end discuss what this represents graphically, and the W1 column that represents the weight attached to the sepal length. The W2 column, this weight, that represents the weight attached to the petal length variable. We now create a new variable called score, and in it we will compute the score based on the current observations. We will use this score variable to classify observations based on estimated weights into either class. So that means into either versicolor or setosa. So we create a new column score, and in it is the intercept plus weight 1 times sepal length plus weight 2 times petal length. This gives us a score of 0, of course, because the algorithm has no idea and has no prior knowledge. We now add a new column that's called prediction. In it, we put in +1 if we think that the flower is based on the estimated weights and its petal length and sepal length, a versicolor flower, and we estimate it as a versicolor flower if the score is greater or equal to 0, and -1 for a setosa otherwise. We create a new column named prediction, and its value is 1 if the score is greater or equal to 0, and it is -1 if the score is smaller than 0. We do so again by using the if function. Now we see that based on our knowledge, so 0 knowledge, our prediction is that the flower that we observe is a versicolor flower. Because of course the score is 0, and we coded it as if the score is greater or equal to 0, that the prediction will be 1. We now continue by computing a different column called error. The error column is simply where we compare whether or not our prediction was accurate. For example, if we know that the flower was a versicolor, so 1, but our prediction was that it is a setosa, we will have 1 minus -1. This will give us an error of 2. On the other hand, this will mean that if our prediction is accurate, the error will be 0. Create a new variable error just by subtracting from the num label our prediction. And we see that in the first case, As we already saw, we predicted a versicolor, and it indeed was a versicolor, so our error is 0. We now get to the core of machine learning. So now the algorithm, it can by itself update its weights. Updating the weights just means that it can incorporate learned knowledge and shift the weights in those directions so as to reduce the error that it made. It tries to reduce the error that it made by a learning rate. If we set the learning rate too big, we might overshoot. Overshooting means that the algorithm will wiggle back and forth too much. And if the learning factor is too low, it takes many observations for the algorithm to learn how to classify the two flowers accurately. Let us continue by creating a new column, learning factor, with a constant value of 0.2. We now perform the updating of the weights according to the formulas on the slides. The weight variable is simply updated by taking the prior weight and adding to it the learning factor times the error. This is simply the formula for the intercept. Now for the weight 1 variable, we take again the prior weight, add to it the learning factor times the sepal length of the former period times the error. This times the error, that just makes it the whole term equals to 0, so no updating happens if no error was made. This makes intuitively sense, right? If no error was made, we don't need to update the algorithm, so we don't need to update the weights. We continue by updating the weight number 2 now. This follows the same logic like the prior weight. This time just with the difference that we multiply it times petal length. The score, the prediction, and the error variable formulas, they stay the same. So we can simply drag and drop them and pull them to the next line. Now what we see here is that in this line, we predicted it to be a versicolor, right? Because it is the same like the first line with 0 information. But however, the flower was a setosa. This led to an error of -2. In the next line, we will see how the algorithm will update its information by adjusting the weights. We can do so by now simply dragging and dropping all these lines because they stay now constant, and we have the formulas which adjust on which row we are at to the bottom. Now what we see here, in the second line it made a mistake, right? So in the third line, now it adjusted the weights according to the direction where it made the mistake. So we had a negative error here, so it reduced the weights. Now in the next line, we again had a mistake. We predicted it would be a setosa, but in fact it was a versicolor. So the algorithm now adjusts again its weights, but now in the positive direction. So we can see this in the weights that go from -0.4 to 0, or -1.72 to +0.72. Now you can observe this on your own. What is striking is that in line 11 here, so in the 11th round of this algorithm, there is a final adjustment. There's a final error. If you scroll further down, you will see that the algorithm doesn't make any errors anymore. So after 12 periods, the algorithm was already to successfully learn this whole pattern and doesn't make any more mistakes when presented with the classification task of a new flower. Now, due to this very simple example and the quite obvious chart that I already showed you, we could have simply taken a pencil and drawn the border. But I told you we don't want to do this. We want to try to make a smart move and let the machine decide and to learn on its own what the pattern should be and where this line should lie. And in fact, the algorithm was able to do so quite well. It estimated the weights for the score equation. Those weights didn't change anymore after the 12th round. If we reformulate that score equation, so we have the borderline at 0, from which it decided if it should be a versicolor flower or a setosa, and we reformulate that score equation and solve it for the petal length, we can actually draw that line that the algorithm computed. Now you see on the y-axis, you have to imagine that the y-axis and the x-axis, it should go until the 0, 0 point on the xy chart. If we would not have an intercept, that means if we would not have a w0 variable, not a w0 weight, we would force this line, this borderline, to go through the 0, 0 point. That means through the point of x equals to 0, the sepal length equals to 0, and the petal length equals to 0. So we lose a lot of flexibility, and we lose a lot of possibility of actually being able to position this line, this borderline between the two classification classes accurately. That's why we need to have an intercept in our score equation. As you might imagine, Rosenblatt's perceptron algorithm is no longer used today. However, you only need to make a few minor tweaks and you arrive at state-of-the-art regression models which are used widely by researchers and decision makers today. In particular, we need to press the score, which we calculated manually, between 0 and 1. This also has the advantage that the score, that means that the predictions from the model can be interpreted as a probability. Now we can already see from the original algorithm from Rosenblatt that there are quite some parameters which we can use for decision making. If you look at the sizes of the weights, you could just say, okay, this weight is bigger, so the variable probably has a bit more influence. Or if this weight is really small, it's probably not that really relevant for the score equation and to obtain the final predictions about which class the flower should be in. You need to, however, just look out for the scaling of the variable. If one variable is on a much larger scale, its coefficient will be automatically larger scaled, even though it might not have a larger explanatory power. Now let's recreate the iris data classification exercise using Microsoft Azure Machine Learning Studio. In order to do so, log on to the website studio.azureml.net. In this video, I already assumed that you have the basic working knowledge of creating a new experiment from the prior video from Introduction to Azure Machine Learning Studio. We now create a new experiment. Please note that in this Experiments tab, depending on what you already did, your screen might look different. But we can always click here on the bottom left, New, and create the blank experiment. Now we can also give this experiment a name here on the top. For example, we can call it My Iris Data. Now we are very fortunate that Microsoft, they already saved this iris dataset because it is such a widely used dataset in data science. This is this iris2 class data. We can simply drag and drop it into this field here. Now if we right click here on this output node, dataset, we can visualize it. What we see here is that we have the original dataset with these 4 variables. Now, if we want to recreate this chart that I showed you in the slides, we can simply go to Visualizations. First, we need to click on the variable. We had the 2 variables, sepal length and petal length. And now we can compare it to the petal length. What we see here now is the same chart that we had in the slides, but here we don't have any indication to which class it belongs. To recreate our Excel exercise, we need to now deselect the 2 variables which contain the width of the sepals and the petals. We can do so by typing in here in the search box, select columns in dataset, and drag and drop this in the field. We then connect this output node to this input node and launch the column selector to select those columns which we still want to keep. We of course want the class, the length, and the petal length. Now if we run this, we can see that the dataset has changed by clicking on the output node of the Select Columns in Dataset module. Now we only have the class variable and both length variables. So this is exactly the dataset which we have in our Excel file. We now continue to create 2 datasets from our original dataset. One dataset is the training dataset, where we estimate the model on, and the other dataset is the testing dataset, where we expose the trained model to the unseen data in order to test how good our model really is on unseen data. We type in split data and drag and drop the split data module to the field and connect it by the nodes. Now what we see here is that we have a fraction of rows in the first dataset, the first dataset being the dataset that is used to train the model. So now we can say 50% of the data goes into training the model and 50% is held out, and on those 50% which the model has not seen, the model will be tested. We can simply use 50% now in this case, doesn't really matter. You will also see a 70-30 split very often used. That means 70% of the data is used to train the model and 30% of the data is used to test the model, how good the fit really is. Next step is to train the model. We need to scroll down a bit now. So we connect this node here, this output node from the split data. So this is the training data set to our train model. Now there's still a value required because we need to tell the model which variable is our y variable, which variable are we trying to predict. Of course, this is the class variable in our case. Now we need to select an algorithm. I already discussed it below. We are using just a variation of Rosenblatt's original perceptron algorithm. So we just squeeze the score between 0 and 1, and that gives us a 2-class logistic regression, which we'll use here. We can drag and drop the module of the logistic regression inside the window here and connect it to the model. After that, we need to score the model. Score model is where the trained model is exposed to the validation data set, so this is here, in order to make predictions on the unseen data. The last step needed to perform a complete analysis is the Evaluate Model module. In that module, a set of common performance characteristics is readily calculated. These include, for instance, the confusion matrix or the receiver operator characteristic curve. We need that module in order to assess on how good is our model. How good did it do in classify those observations? Here we already have the evaluate model. You can now simply drag and drop it below here. Now we see here in the evaluate module, we have two input nodes. We use this if we want to compare multiple models against each other. What we can now do is we can run the complete model. We can now look at the results by right-clicking on evaluation results on the output node of the evaluate module and clicking on visualize. What we now see here is the receiver operator characteristic curve, and we see a perfect fit. Means we have a true positive rate of 100%, and we do not need to make any trade-off between having false positives and the true positives. What we also see here is the confusion matrix. So this means 29, that we predicted that 29 would be a default, and they indeed were a default. True negative ones are that we indeed predicted that we had 21 setosas, and those 21 predictions were indeed setosa flowers. The errors would be here. This one, for instance, would be a false positive. A false positive means you predicted that this would be a versicolor, although it in fact was a setosa. A false negative means that you predicted that it would be a setosa, but in fact it was a versicolor. What we need to pay attention to is the probability cutoff for the score. Now, what we see here is, we already mentioned that the score of the logistic regression, it is squeezed between 0 and 1. So that means that all observations that have a score of greater or equal to 0.5 are classified as a versicolor. All observations with a score of less than 0.5 are classified as a setosa. What we can do now is we can just move this threshold up and down and see what happens to our errors here in the confusion matrix. So for instance, now we have a cutoff point of 0.8. What happens now is we only have 4 true positives. So we are much more restrictive in which observations we will classify as a versicolor. This led to 25 false negatives. So 25 observations were not able to be classified as a versicolor due to our really high probability cutoff. And these 25, even though they are actually versicolor, were classified as a setosa. And this is what is known as a false negative. Obviously, the optimal case is that one doesn't have any false positives and no false negatives. But this is rarely the case if you do this analysis in practice with real data. So then the question is, how do we set this threshold parameter? Setting this threshold parameter is just, in the end of the day, it's a business choice. Because in order to have a lot of true positives, we also need to be able to accept that we will have a couple of false positives. Where we set the threshold does depend on the costs of the misclassification, namely on the costs of making these two specific kinds of errors. At the end of the day, business people need to make these decisions and not data scientists. That's where the role of management comes in. Thank you for watching.